Here today is Usman from Stats. I'm sorry, we don't have a clicker. Someone stole it from this room. Yeah, sorry about that. Yeah, he's going to talk to us about branching processes and approximations.
Cool, thank you, Sasha. As the title says, I'm going to be talking a bit about branching processes, giving a fairly basic introduction to them about discrete continuous time, and then talk a little bit about some ways in which you might want to approximate certain properties of these branching processes. So, kind of like I said, we'll start with discrete time models. So I guess very generally, branching processes, they fall into the class of stochastic processes or objects evolving randomly in time. So we can either take space or time to be discrete or continuous, depending on the type of problem we're working on. And they're going to model phenomena where particles are going to move through space, and then at some other deterministic or some random time, the particle is going to die and then produce some random number of offspring, and it could be that that number of offspring is either located at the point at which particle dies, or maybe it's non-local in that particle, when it dies, produces offspring in a non-local way. So certain areas of application might be like within biology and physics. So one example is epidemiology, for example. If you're trying to model the spread of a disease through a population, you might have heard of the SIR model. That can be understood as a branching process where an infected individual will move through space and then infect other individuals locally around them with some probability. Other areas in biology might be like a cell division. They're trying to model how cells divide, and some kind of synaptic cell division generally. And then another application which more pertains to my research is physics, in particular looking at nuclear fission. So in this physics application, you have a neutron moving through a nuclear reactor. With some probability it might die if it hits the boundary of the reactor, or with some other probability it might hit another neutron and then undergo a fission reaction. And you can model that fission reaction as this random number of offspring being distributed non-locally in space. So I guess if you start very basically, if you kind of recall your first year probability, then you probably would have heard of the BGW, the Galton-Watson process, which is probably the most basic example of a branching process. So here, you've taken time to be discrete, and you've taken your state space to be naturals and naught, and what you do is define a family of IID integer value random variables, so these xi superscript n, where that's going to tell you the number of offspring an individual will produce when it dies. So we start with n naught being 1, and then capital N, little n is going to be the sum from I equals 1 up to nn minus 1. So all individuals in the previous generation will produce in an IID manner some number of offspring. And because we're looking at what happens from time n to time n plus 1, what happens after one generation, you can see time as generational as opposed to real in this sense. So again, kind of recalling your first year, maybe second year probability, if you want to understand certain properties of this BGW tree, one such thing you might want to understand is this extinction probability. So I denoted it by zeta, where zeta is the first time your branching process hits 0. Then one thing you might remember is that if you define q to be the probability extinction happens a finite amount of time, and you define mu to be the expected number of offspring you produce at death, then there's this correspondence where the extinction probability is almost surely finite if, the extinction probability is, I think I might have my q's being greater than or less than 1 the wrong way around. It should be that if mu is greater than 1, there's some non-zero probability that your process will not die in finite time, whilst if mu is less than 1, then you would expect an exponential decay, which means this extinction probability will be 1. Oh no, I did do the workaround. Okay, cool. And then another thing you might remember is that you can kind of infer more information about this q value by looking at the probability generating function of the offspring distribution. So in essence, if you look at this polynomial in S, it turns out that q is the smallest solution to this polynomial expected value of S to the x, IM equaling S, which is again something you might remember from first or second year probability. So the thing about the BGW is that it doesn't really allow for the modeling of spatial movement like we were talking about before. The example of neutrons, it doesn't allow you to model the movement of a neutron through space. So if you want to adapt our branching processes to allow for movement in space, we're going to have to introduce some Markov process where we're going to define a measurable state space E, and then append onto that state space this delta, this kind of partial del, where we're going to then let X be a Markov process with transitions given by a family of Markov transitions Mn, and in the case where time is homogeneous, we'll just index this Mn equal to M. But effectively, if we're at time n minus 1 at location X, we end up at location Y according to this Markov transition. What we'll say is that this process X associated to our Markov transition M with probabilities given by bold P, where this little x will determine just the initial location of our Markov process. And what this last line says is where this kind of appended cemetery state comes in. So with some positive probability, it might be the case that our Markov process will die in finite time. And if we denote by tau this death time of our process, we're going to let delta be the cemetery state. And once our process dies, it stays in the cemetery state for all times little n greater than tau delta. So that's how we're going to model spatial movement for our branching process in discrete time. And now to model offspring, well, for the BGW, we were just considering the number of offspring we produce, but now we're wanting to model spatial locations as well. And if we're wanting to model spatial locations, one way in which you can do that is by understanding the locations in space at which we deposit our children as a random counting measure. So what this z subscript x is, which is the sum from I equals 1 up to some capital N of delta xi, is a counting measure that's going to tell us the locations in which we're going to distribute particles within our phase space at that. And we're going to denote these with laws Cali B and expectations Cali E. And what we're also going to do is say if we take z to be 1, then the expected number of offspring at a location little x is going to be denoted by this capital G function. And importantly, if the process is in the cemetery state, we don't produce children because that means our Markov process has already died. So, kind of what I said already, this Zx, if we put in 1, it just tells you the random number of offspring the particle will produce, and then this Gx is the expected number of offspring, where importantly, it depends on the location at which we die. So then, from here, we can kind of build up a branching process quite naturally. I can also draw out, whilst I'm explaining what's going on. Okay, so quite simply what's happening here is that we're initializing some location x, which is x1 times 0, to be the initial location of a particle. A particle will then move according to that Markov transition M1 we were talking about until it dies at some random location given by the endpoint of our Markov transition. So we'll move through space and then end up at some point given by what we call the x1, 1 minus. So this 1 minus is basically saying we haven't undergone branching yet. This is just the location at which we die after one generation. And then given that at that location x1, 1 minus, we're going to produce children according to this random offspring function z index of at location x1, 1 minus. So in this case, we might produce 3 children where these three children are our zx, 1, 1 minus. And then from there, what's important is that each of the children are going to evolve in an IID fashion similar to as a parent did, which means they're then going to undergo this algorithm again, where they're going to evolve according to the Markov transition indexed by M2 now, or if it's homogeneous, just M, and then produce children again according to Z, depending on where we die in space. So if we then track the location of all of our particles at time n, then kind of similarly to how we wrote the offspring distribution as a random measure, we can write the branching process itself as a random measure, which means this curly h at time n, being the sum from I equals 1 to n of these delta xims, is now the location of configuration of our particles after n generations of, I guess for the neutron example would be fission, but I guess n generations of producing offspring. And because it's a measure, typically we're going to act on some test function f. Once you act our measure value process on a test function f, this then just becomes some real values process. So for instance, if we just take our function f to be 1, and if we're in the case where our offspring distribution zx didn't depend on the location in space, that would just mean no matter where we were in space, we just produce children in an IID way, and if the number of children we produced was then just some random number that didn't depend on the spatial location, the number of offspring we would have at n generation would be equivalent to our BTW that we had before after some tools. So this curly HN is what I'm going to call a generational branching process. But in some areas of application, you don't want to think about time in a generational sense. You want to think about it in a real sense. In other words, if instead of at time 1, maybe you don't want to be at the point at which you're going to do fission, maybe you want to actually be able to track what the location of the particle is at some real time t, then all we're going to have to do is augment our Markov chain to be some Markovian process indexed by the positive real line. So we're going to do this fairly naturally just by replacing our Markov transitions M with some semigroup P indexed by little t, again on our augmented state space E appended with the cemetery state delta. And we'll say that if we start at position 0 and then at position t going from x to y, then that's what our semigroup is going to tell us. And we'll naturally write that if our semigroup acts on a function from the right, it's done in this way, whilst if we use a measure, it's going to act on measures on the left. Then the process xt associates the pt that again we're going to say has probability of bold p, indexed by little x being the starting position, and again we have this def time of our Markov process, which might be in the neutron case, again hitting the boundary of a reactor. And then again, once we're in the cemetery state, we stay in the cemetery state for all times after then. So now what we also want to be able to do is try and model out what time branching is going to occur. And a very common model for this is where you take time to be kind of exponential, but perhaps dependent on the state space. So what we're going to do is say that on our state space there's some function beta mapping into the positive reals, which is known as the branching rate. And what this is going to tell us is that if tau b is the branching time of a single particle, then it has this property that tau b happens after time little t, given the path of the process up to time t is going to be exponentially distributed but spatially dependent, which is why we're integrating from 0 to t minus beta xs dx. And again, if beta was constant, that would just be an exponential random variable with parameter beta. And then from here, the construction is pretty similar to how we did it in discrete time. It's just going to be that our initial location be little x, and we're going to move the Markov process with our transition operator up until this time tau, which is either the first time we die according to the Markov process or the first time we branch. So if tau is that first time, we're going to let x1. This is now going to be x1 tau minus instead of x1 1 minus. But apart from that, everything's the same. We just run up until the first event time, tau, and then produce offspring according to our random offspring distribution. And then, as we did before, we can understand this as a measure-valued process, where now time is just indexed by t instead of n in the naturals. So y is going to be our real-time branching process, we called it. And then again, this is going to act on test functions f. So one kind of, I guess, probably the most famous example of a continuous time branching process is probably the binary branching Brownian motion, in which your Markov transition is now just taken to be that of a Brownian motion. Your Markov semigroup taken to be that of a Brownian motion, and at a def time which occurs at rate lambda or rate 1, you just produce 2 offspring at the location you are. So when a particle dies, you produce 2 more particles that then go on to evolve as Brownian particles, so you expect like exponential behavior over time. And in this example, you can see perhaps there's some positive probability you die. So it might be you produce 2 children, or you might produce 0. So I mean, when it comes to actually characterizing these objects, like I guess remember that when we act our measure value process on some function f, we just get a real value random variable, right? And if you remember from your first year or second year, you can characterize a random variable by its Laplace exponent, which is this eta minus theta acted on our random variable hn acting on a test function f. And typically you want to see how this, you want to characterize this object as theta ranges over, that's either the complex, let's say the complex numbers or the real numbers. But obviously theta can just be passed into our branching process H. So really, if we just define this V object as this nonlinear semigroup, we call it, then you can characterize the law of the branching process by looking over a large enough set of test functions, where that set of test functions will depend on the properties of the branching process itself. And this V is known as the non-linear semigroup. And I think one thing I have forgotten is that this V should be indexed by little n because it is dependent on time. I just forgot to put that in. So that's how you probably characterize the law of your branching process, but sometimes you don't really care about all of this information given by the exponent. Sometimes perhaps you just care about the first moments of your branching process, because let's say in the neutron case, you want to understand after one generation of fission what the expected number of particles you have in your system is, because you'll want that to be close to 1. Otherwise, your reactor will either die out in finite time or blow up in finite time. You don't really want it to blow up in finite time. So what we're going to do is try and understand this linear semigroup I called Q, indexed by little m, that acts on functions f, which is just the expected value of h and acted on f. So what it turns out is that, let's say you wanted to simulate this branching process, then there are kind of multiple ways in which you can simulate this branching process such that you get agreement with this Q. And one such way is known as the many to one formula, where maybe if you just think of a basic example, let's say we take our G function just to be spatially homogeneous and say it's equal to 3, and let's say our Z function is just 1, where we always produce 3 offspring at the same location as the parent. Then what happens is, in this example, we're going to go along, move through space, we'll produce 3 offspring, which will then go on to move in space, and then go on to produce 3 more offspring. So what we can do instead of actually producing all of these branching particles is say, just evolve one particle according to our Markov transition, which is where this bold E is coming in. Remember, bold E was the expectation with respect to our initial Markov transition. What we can do is just append the weight of 3, which again is equal to g of x, to our particle, and then keep moving it according to our Markov transition. So this time, which will be x11, we append a weight, which would be the expected number of offspring we would have expected to see. What we do is, instead of actually simulating that number of offspring, we just append the weight onto it, and then at this time, we'd append a weight, what, 3 squared, after 2 generations of fission, and then maybe after 3 generations, we append on 3 cubes, because at each of the fission times, we're just going to append on the weight we would have expected to see. And what this is doing is basically a way of approximating, well, a way of writing out basically the center of mass of this branching process in terms of one particle, with a weight appended onto it. So that's kind of the heuristic behind the many to one formula, that we're taking this one particle and moving it through space, appending a weight onto it. So now I'll talk a little bit about other ways of approximating the linear semigroup. So kind of what I said before, the center areas of application, we care about estimating this linear semigroup and linear functional of our branching process. So the example that I worked with is nuclear fission. In this example, we take our state space to be some D cross B, where D is going to be some bounded subset that will tell us the domain of our reactor. And this B is basically the space of valid velocities our neutron can have. So what's happening here is that we have a particle, a neutron moving through space up until the fission time, and then at a fission time, you're going to produce offspring at the same spatial location, but with different velocities, because after a fission, you produce new fissile particles with different velocities, so they'll go in different directions and also have different overall speeds than the parent is. So it's non-local in this sense. And then this Zx will represent the random fission offsprings produced in a fission reaction, and this Q will tell us the expected number of neutrons after n generations of fission. And then it also turns out that for this Q object, under certain conditions, we do have nice ergodicity properties, where effectively we have the existence of some lead eigenvalue, which we'll call K effective, some left eigenmeasure, omega tilde, and right eigenfunction, omega, where if the angle bracket is just the integral between two functions, then we have the standard way in which eigen vectors interact with operators for omega tilde and omega. So, I mean, like I said, all nuclear engineers want to estimate this K effective, which is this instationarity, expected number of offspring you produce after one generation. So, like I talked before, you can either maybe simulate the whole branching process, maybe you want to do like a bunch of IID simulations of the branching process, or maybe you want to do a bunch of IID simulations of the many to one particle. But, I mean, this object over here is going to be computationally expensive, especially if you're in a supercritical case, because as time evolves, the number of particles you have to keep track of is growing exponentially, even though it will have like a lower variance, whilst this object, you're just tracking one particle, but because you're appending one particle with a high weight, its variance is going to be quite high. Like, I mean, if you have the variance of just n particles that are IID, that's just for n times the variant of x1, whilst if you have the variance of n times x1, that's going to be now n squared variance of x1. So you might have two cases where you have two simulation methods which are unbiased, but maybe one's more computationally expensive, whilst the other, whilst easier to compute, is going to have maybe order n squared greater variance. So maybe there's some way to kind of work in between these two methods, and it turns out that it's one way in which you can is do what's known as a selection evolution type scheme, where effectively what we do is kind of something in between what's going on here and here. So what we're now going to do is specify some capital number m to be the number of particles we're going to simulate. So maybe I'll take m equal to 3 here. And we're going to initialize 3 particles, psi1 and psi2n. So psi1 naught, psi2 naught, and psi3 naught. What we're going to do is a selection evolution type scheme where effectively, it doesn't really matter which way around you do the operations, but if this g, remember, was the expected number of offspring we produced at a location, we're going to weight each of these particles according to the expected number of offspring it would have produced, and then do a selection to say, instead of branching or just appending a weight, let's say we append the weight 3 here, append the weight 1, and then append the weight 5. We'll do a resampling step where it's just multinomial according to these weights 3 times. So maybe we sample this particle again because it has a high weight, and then maybe we sample this particle, and this particle doesn't get sampled because its weight is smaller than the other two. So we'll call this psi hat 1 naught, psi hat 2 naught, psi hat 3 naught. So this is kind of in between simulating all the particles and depending the weight, because it's meant to approximate that branching step, which is what the selection step 1 is saying, and then the mutation step is just saying we evolve each particle according to that Markov transition we were working with before. So in this example, we're approximating the generational branching process, but similar methods exist for continuous time processes as well. So from here, we're then going to evolve our captive particles up until the death time according to that Markov transition. So this will be psi hat 1 naught, and then we'll just do the same for the other two. And this is known as a kind of selection evolution type scheme. If you've ever done like sequential Monte Carlo for particle filtering, then this is equivalent to like a particle filter where instead the weight would correspond to laws of conditional probabilities of your observation given your underlying random variable, but the idea is the same. You're weighting particles, selecting them to approximate the branching step, and then doing an evolution according to your Markov transition. And this again is another example, another diagram to say the same thing, where this curve here, if you take, let's say, your domain just to be the real line, then this curve is going to be your potential function over the real line. So, see, for example, this particle is in a space where potential function is high, so maybe you produce a lot of offspring here because this is where a fissile rod is in the reactor, whilst at the boundary over here you have an absorbing medium, so the expected number of offspring is small. You're going to move your particles through space, weight them, and then do selection according to those weights. So, I mean, a lot of work has been done to analyze these very basic kind of selection mutation type schemes. And I mean, a lot of results exist already, kind of as of about 20, 25 years ago on these very general selection mutation type schemes I kind of found in this textbook, cited by Delmore in 2004, that looks at approximating prime and cap formulae using these selection mutation schemes. So if you define eta as capital M little n to be the configuration of our m particles after n steps of this operation, and then you define gamma to be a weighted version of this, that then is in an attempt to make the algorithm unbiased, then there are a lot of theorems that exist about the bias and consistency and also central limit theorems for these types of objects. So I just put one example here, which says that, remember that Q semigroup we were talking about, we have that weighted algorithm is unbiased, and we also get an almost short convergence of the weighted and unweighted algorithm towards functionals of the semigroup. So gamma approaches Qn whilst eta approaches Qn once it's been normalized. And then we can also control the LP norm, p greater than 2 for the normalized algorithm as order 1 over the square root of m. And then if you look at the first and second moment, or first and second LP norm of the normalized algorithm, it's again order 1 over m for equal 1 and order 1 over root m for p equals 2. So that's just some examples of theorems you can get out for these basic selection mutation type schemes, but the algorithm we just described is just one example of this kind of type of algorithm where you do some selection step and then some mutation step. And there are many other variants that have branched off from these type of basic schemes. So what I look at, which I'll talk a little bit about, is an algorithm which is known within the nuclear literature as superhistory powering, in which what you do, instead of just, in this example, simulating a Markov transition M of a one generation efficient, you're going to set some parameter L to be your number of generations efficient, and then simulate each of these sample particles to L generations efficient, and then do some kind of selection normalization step in order to control the number of particles. So in this example, what you have is that we start at time n here, do some sampling, just uniformly evolve each of these particles according to a branching process. So in this example, this particle dies, this particle dies, this particle goes on to produce 4 children, and then if you end up with more than n particles, in this case n is 3, so in this example we, let's say, throw away particles uniformly at random until we have 3 particles left, whilst if we're in the case where, let's say we have less than m particles, after branching, then we'll just duplicate particles in an unbiased way in order to refill our sort, so that's a fixed size. So kind of heuristically, you can see the scheme falls into the same type of structure as the one we described before. It's just a little bit more complicated, but what I've been able to show so far is that a lot of theorems kind of similar to the one I showed before about kind of law of large numbers, LP bounds, LP convergence, central limit theorems also hold for schemes like this. And then I think what I'm aiming to do is try and compare exactly what the effect of branching on an algorithm like this is, and also see if there's maybe some optimal parameter for the number of branching steps when you want to account for balancing, variance, and also computational efficiency. So I think I'll just stop there. If you have any questions, feel free to ask.
Thank you, Usman. I think in the interest of time, we might do questions over cake. Yeah, there'll be cake in the master's common room now. Everyone's welcome to join.